Hi there. This video is going to walk through a couple of examples for using term symbols. So the first example we're going to look at is the question, what are the possible values of the term symbols for the 1s1, 2s1 configuration of helium? Alright, so here we have a situation where we have two non-equivalent electrons. Okay, so they're in different orbitals. So this would fall under our non-equivalent electron category. Okay, so we don't have to worry about the Pauli exclusion principle here. Okay, so we just can go ahead and put our Clebsch-Gordan series approach to use. So first thing we want to do is to assign our little l value, so little l for electron 1, so that's in an s orbital, so we're going to get a 0 for that. And then our second electron, also in an s orbital, so we'll have a 0 for that as well. And we might as well assign our s's, our spins as well. So the spin for electron 1, we're going to say is plus 1/2. And again, spin for electron 2, also plus 1/2. Okay, so remember, convention is if you have the ability, give your electrons the plus 1/2 designation. Okay, so in this case, each of our electrons is in a different orbital, so both of them have the opportunity to be spin up, so we are going to make them that way for our Clebsch-Gordan application. Okay, so now we will go about doing our Clebsch-Gordan series. So let's calculate our big L. So L1 plus L2, L1 plus L2 minus 1, truncata L1 minus L2, absolute value. So if we put in our L's, oh, this one's nice and easy. So they're both 0, so only option we're going to get out for L is 0. Okay, so that's going to correspond to an S designation, we know. Let's see what happens with our total spin angular momentum options. So again, here we want S1 plus S2, S1 plus S2 minus 1, so on and so forth until we hit S1 minus S2, absolute value. So there we would get options of 1/2 plus 1/2 is 1, and then we can go 1/2 plus 1/2 minus 1 is 0. Let's double check where we truncate at 1/2 minus 1/2 equals 0. So that's as far as we're going to go. Remember, no negative values should pop up for either your S or your L when you're finished. Okay, so this is going to lead us to two different options for multiplicity. So remember, 2s plus 1. So we're going to get a triplet for our s equals 1 option. And we'll get a singlet for our s equals 0 option. So when we put everything together, we should end up with two possible term symbols for this configuration of helium. So we should end up with a singlet S and a triplet S for this particular example. Okay, so let's do another example. This time we're going to look at the atomic levels for the electron configuration of the form NS&P. Okay, so remember, levels indicates that we're taking into account the spin-orbit coupling, so we're going to have J come into play here. So don't forget to include that. That's going to go in the subscript of your term symbol notation. And then note that we've got one electron in an s orbital and one electron in a p orbital. So again, we're going to have the situation of non-equivalent electrons. Okay, so again, we don't have to worry about our Pauli exclusion principle in this case, so that makes things nice and easy. We can once again go ahead and use our Clebsch-Gordan series approach. Okay, so as usual, we will assign our L's and our S's for each electron in our configuration. So L1 here is in an s orbital, so that's going to get a value of 0. L2 for our second electron is in a p orbital, so that's going to be a 1. And then let's do our spin. So the spin for electron 1 we're going to say is plus 1/2. Okay, and then spin for electron 2 we're going to say is also spin 1/2. Again, remember, we've got non-equivalent electrons. We don't have to worry about the Pauli exclusion principle in pairing our spins. So each electron's in a different orbital. Both of them have the option of being spin up. So remember, that's our convention when we're using that Clebsch-Gordan approach. Okay, so let's figure out our L's. So L1 plus L2, so we're going to have 0 plus 1, 0 plus 1 minus 1, all the way to 0 minus 1, absolute value. So we're going to get options of 1 and negative 1. Absolute value of negative 1 is 1, so we truncate at 1. So careful that you don't go on autopilot like I almost did. We only get a value of 1 there. Okay, because again, that series is going to truncate at 1 for us. All right, let's do our S. So S1 plus S2 is 1/2 plus 1/2. 1/2 plus 1/2 minus 1. Down to 1/2 minus 1/2. Okay, so we know we're going to truncate at 0. And then we're going to have an additional option of 1. Okay, so we get options for S of 1 and 0 from that series. Okay, and this time we're going to add on one more series to get our J. Okay, so remember, we're doing atomic levels in this example, not terms, so we want to include that spin-orbit coupling. Okay, so remember, J is given by L plus S minus 1. If you haven't memorized the Clebsch-Gordan series at this point, it's probably in your brain whether you like it or not at this point after these two examples, but we will truncate at the absolute value of L minus S. Okay, so our truncation is going to be L minus S. We're going to get truncated at 1 in that case, so 1 minus... Oh, wait, we've got 2 different values of S. Okay, so we will do this for both options. Okay, so we have 1 minus 0. So we'll get 1, and 1 minus 1 equals 0. Okay, so we will have L plus S for the S equals 0 option. So 1 plus 0, 1 plus 0 minus 1, all the way to 1. So we will get options of 1 and 0 for those first 2 terms. And then we just have to note here, careful again, don't go on autopilot, we're going to truncate at 1. Okay, so we just get the 1 value here, of J, and then same with our other value of S. So we've got 1 plus 1 1 plus 1 minus 1 until we hit 1 minus 1. So we can go all the way down to 0. So we're going to get options of 2, 1, and 0 for this particular combo of L and S. Okay, so again, just be careful here for the J. You have two different combos that you have to account for. Okay, so we've got the 1 and 1 combination of L and S and the 1 and 0 combination of L and S. Okay, so here for this particular combo, we're going to get our L's are all the same, right? L equals 1, so we're going to get a P symbol for that. And then our multiplicity, in this case, this example is for the S equals 0 option, so we'll get a singlet on there. And then the J that corresponds to that combo is this calculation here, so we're going to get a 1 for the J. Okay, and then for this combo of L and S, so that's our L equals 1, S equals 1. So I'll just make a note here that these are for our two different combos of L and S. All right, so we get options. Again, we're still just dealing with P because our L equals 1. We only have that one option. But now we have a different multiplicity. So for S equals 1, that gives us a triplet. Okay, and then we're going to have 3 values possible for the J. Okay, so we'll have 3 different term levels that correspond to those 3 different J's. So we'll have a triplet P2, a triplet P1, and a triplet P0. Okay, so when all is said and done, we end up with 4 possible term levels for the NS-NP electron configuration. All right, so again, just a couple things to look out for in problems like this. Again, pay attention to where your series is truncating, okay? If you have multiple values of L and or S, okay, you're going to have to do multiple series to get your J values. Okay, so we've got 2 different sets of J calculations because we have 2 different options for the S. Okay, so that leads us to our singlet P1 from our first set of L and S values, and then we get 3 additional levels from the other combo of L and S. All right, so again, just take it step by step. Be careful not to go on autopilot with your series. Okay, they don't all have to end at 0, and that should get you to where you want to go in identifying your atomic levels. All right, I hope that was helpful. Just a couple practice problems using these atomic term symbols and level designations for various electron configurations. Thanks.